Okay, well, this is a very different presentation, tangentially related to the one that we just saw. Obviously, teachers ultimately work with crafting modifications of the human mind. That's what education does. So I have a little visual bibliography here. These are several books that I like to recommend to people for reasons that will become evident as we move through this. So I have about 3 pages here where I'm just providing you with an advance organizer of where this talk is heading. And I'll just click through these pretty quickly. I consider myself somewhat of a cultural historian, but I also have an interest in cognitive neuroscience and in a field called cognitive archaeology, which is an effort to understand how the brain evolved and then how we ended up with the various capabilities that the brain has, all of which were evolved in very different circumstances from what we live in today. We're in a humanly created, purpose-built environment. And this means that we have managed to retask some of the functions of the human brain, the human mind, to do things that they did not do originally. They have been adapted to language, for example, symbol use, tool use, and a number of other capabilities. It is fascinating to me that we developed the capacity to use tools. That was a long time ago that began, earlier iterations of hominids. But we have this notion from Vygotsky that tools for the hands mediate physical actions. Tools for the mind mediate cognitive actions. And as we develop more tools for the hands, we can do more things with the hands. And by analogy, as we develop more tools for the mind, then that repertoire also expands. In trying to study human psychology, Vygotsky was raised as a behaviorist, but he realized that that doesn't really get us into the more interesting things that the human brain and the human mind do. And so he began to look at this particular model and recognize that there is a coevolution of culture and cognition. As we expand the repertoire of tools for the mind and intellectual or cultural systems, we're actually transforming human consciousness, human cognition. Memory is a residual thought. This is I've got several sort of principles that teachers would be interested in, and this comes from the work of Willingham. He wrote a really nice little book called Why Students Don't Like School. And he makes suggestions, and one suggestion is think about what your students are actually thinking about, because the things they think about will be the things that get embedded into memory. The idea that perception is an active process, this came originally from the Prussian philosopher Kant, who recognized that perception is an active cognitive process. We don't receive images ready-made. We construct them on the basis of a chaos of sensory input. This next notion comes from Gestalt psychology, that the mind is a pattern-seeking and a pattern-making mechanism. And this has implications for curriculum design. We have tended to break things down into particles of knowledge, define them behaviorally as instructional objectives, and then teach them in a disaggregated kind of particle by particle fashion. But what the mind wants to receive is a big picture. How does this all fit together? And, the old teacher saying that this will all make sense in the end is not very helpful. The overview has to be provided really from the very beginning. Episodic memory, this is something that Merlin Donald added to our repertoire of ideas and terms, that human experience is episodic, and we capture it as episodes. Damasio has promoted the idea that cognition actually begins in the body with feeling and the rudimentary aspects of what all mammals are capable of doing. The body contributes to the understanding that the mind is forming. And thirdly, affective states, and this is part of what happens in an episode. You're being chased by a tiger. There's a very definite feel to that. You are walking among wildflowers in a peaceful, warm, sunny day. There's a definite feel to that. And those feelings are important in the formation of memories. Experiences encoded by the amygdala on the basis of the emotional valence of those feelings. So as we teach in school, if the things that we're presenting are just sort of dry and factual, there's a very low emotional valence, if not a negative valence. So teachers then are, in a sense, challenged to make it interesting somehow, make it relevant. And one of my suggestions is that we can make it episodic in nature by the magic of storytelling. Humans are social creatures. We know this. Every teacher understands this. It is a critical component of the learning experience, how we have fashioned the community of learners and the nature of the social contract that exists among them and between them and the teacher. Humans developed language a long time ago to serve the cultivation and development of the social learning group, of the tribe, of the band, if you will. And in turn, language alters human consciousness by putting a reflective loop into it. We're able to think about our thoughts when we have crystallized them into language and other representations. There's also a sense in which we think through the medium of languages. Natural language, as we are communicating with each other here, the thoughts that we're having are encoded in language. But it's also the case that we think through other systems, other cultural systems, such as mathematics or science or music or art. And this is part of the original insight of liberal education that we have tended to lose sight of. These different subjects that we teach to students, they are the major languages of the mind, if you will, the major frames of understanding and modes of experience. We don't really cultivate that understanding with students. That would be part of a meta discourse over and above the actual teaching of the content. But this is part of what I have tried to promote through my work. The advent of writing was what I refer to as a primary transformative event, when you were able to crystallize your thoughts. And in writing, that means you have turned them from a subjective experience to an object that is now external to you and semi-permanent. And now you can look at it, you can reflect on it, you can do a whole course of other thinking, and that thought will still stay there in front of you as a body of writing. So that is an interesting feature of this literacy that we teach. Writing also serves as an extension of our long-term memory. It's different, but these books that are behind me on the shelves, those are the thoughts of other people, many of whom lived hundreds or thousands of years ago. But I have access to those, and I can add those things to my repertoire of experience by reading those books. Writing was not developed for most of human history. In fact, it was only after the close of the last ice age that humans got onto the business of settling in communities and growing food. And the great river civilizations of the really big cities, such as we find in Egypt or Mesopotamia, or in China or in India along those rivers, those are the places where writing was developed for the sake of record keeping. And then it got retasked for other creative purposes later on. The alphabet, arithmetic acquired the benefit of symbolic notation systems. If you've ever tried to multiply with using Roman numerals, you know it's pretty clumsy. So the quality and the nature of the cultural technology is of importance in the discussion. Okay. So that is my overview. That gives you a taste of where this heads. And this is somewhat of an eclectic presentation, so bear with me. This is a heuristic device. For the first 10 years of my career at MSU, I was teaching educational psychology to elementary education majors. They are K-8 and they cover all subject areas. And part of what I wanted to do was help them think about the subjects that they teach in a way that is a bit more historical and humanities-like, if you will, from what they will get in their methods classes, where these beautiful bodies of knowledge, mathematics or art or literature, are being converted into subject matter. And that is a significant achievement of the education profession, the ability to disaggregate and break down these systems of knowledge into particles that can be defined behaviorally as standards and then taught and then assessed. That's how the teaching profession operates. But in the process, we end up pulling them out of context and turning them into something very different than the lived reality that the scientist knows, or that the mathematician knows, or that the artist knows. And if we are to take an expansive view of human history, and in particular human cultural history, these are remarkable achievements. And there is a basis there for a deep aesthetic appreciation of these subject areas. And I like to refer to them with the old term, intellectual discipline or academic discipline. Subject matter is a kind of lumpen, proletariat, materialist term, if you will. But we have to think about it both ways. So this is a heuristic device that I used, and it went something like this. Imagine that you are a middle school teacher and your subject is represented along the left-hand side of this diagram. And the idea is, in the 3 years of middle school, we are going to proceed across the historical timeline and teach the subject in historical context. And so you will see in this first column the development of a mathematical mentality, the very beginnings of it, of arithmetic, and of early counting systems and number systems and so forth. And then in the second half of that year, you're going to study geography. It arose in Greece. Geometry. It arose in Greece over a 300-year period of that classical civilization, so forth and so on. And so trigonometry and algebra and all of these subsets of mathematics, they had a developmental history. They were created by people. And the second part of this heuristic is in any given field, let's take geometry, for example. With a British colleague named Stuart Rowlands, he's a mathematician and a math educator at the University of Plymouth. We analyzed classical geometry, and we were looking for the major cultural leaps that happened in the history of that field. And I'm going to share some of that with you. Surprisingly, we were able to account for the cultural historical evolution of geometry in just 17 of what we call primary transformative events. So the kind of saltatory leaps that make the science or make the art or make the mathematics evolve to a higher level. There are few of them in any domain, but they're critically important. They're important for understanding the historical development, but those conceptual leaps are also cognitive transformations that every learner has to go through in order to go from the normal novice state to the advanced abstract current or later day state, if you will, of those professions. I'll come back to math. I knew there'd be some science people here. So this is a nice representation here of a transformative event, a primary transformative event in the development of physics. This is a device, and I don't think it's original, but it's a nice replica at least. It is in the Science Museum in Florence, Italy. And Galileo designed this to be able to study the effects of gravity on an inclined plane. So if you see the chain at the back, the left-hand side of it, he would pull that chain, it would release a steel ball, and the ball would roll down this ramp. Along this ramp, he had located 5 bells, like this one here. When the ball rolls past it, it trips this little thing, it dings the bell, but this mechanism doesn't slow the ball down, it just keeps going. So you release the ball, and also these bells can slide up and down the ramp, and then there's a set screw on the backside where you can tighten it. And what he wanted to achieve is adjust these bells, the location of them, so that when he released the ball, there would be a steady ding, 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 right? This is where they ended up. And so what does this tell you about the nature of motion as that ball is rolling down this ramp? It's picking up speed, right? It is accelerating. And so there is change, that is to say, the ball is moving from one location to another, but there are also changes in the rate of change. And eventually he would study the falling bodies and be able to calculate that they fall at 16 feet per second. Aristotle had been the authoritative word on this for 1,500 years. Aristotle, in Book 7 of the Physics, said that heavy objects fall faster than light objects, and when you drop an object, it hits its terminal velocity instantaneously. And Galileo had the audacity to question that grand tradition and eventually overthrew it. So in this mechanism that you see, there are 2 primary transformative events really that are identifiable together. One is the fact that Galileo created a controlled experiment. This is a first. And the other is he made observation. Aristotle made observations also, but Galileo made them in such a way that they could be quantified. And therefore, he collected quantitative data, numerical data, and he analyzed it. And so what we now have is the introduction of experimental, controlled experiments and the mathematization of science. These are examples of what we would refer to as a primary transformative event. So going back to this little heuristic, and I'm always careful to say to students, you're not going to teach out of a curriculum that looks like this, but this is a model of curriculum and of culture that can run parallel to each other in your thinking. And so it's a good model to have in mind as you think about the subjects that you teach. You don't just think about them as school subjects that have been reduced to an inventory of individual instructional objectives. Think of them as human achievements that are embedded in this grand human cultural experiment that we call culture and civilization. And when you do this, you begin to see things in a very much more interesting context. As you look at a given historical period, what you find is that these disciplines are talking to each other. So ideas that are created in one of them will transpose metaphorically across disciplinary boundaries, and the culture itself will end up with a kind of characteristic quality and flavor, character to it. That is the cultural style, if you will, of classical civilization or of the Renaissance or modernity or the age that we live in. And the other thing is that as you go this direction, you're seeing the evolution of a set of related ideas that continue to grow and evolve organically. And occasionally you get a saltatory leap because of some new discovery, innovation, the creation of a new convention, the introduction of the alphabet altered writing, for example. The introduction of base 10 and place value altered arithmetic, and so forth. So here's you can read this. This is a kind of prototypic student complaint. I don't understand why I'm doing this sort of thing. Why do I need to study geometry? And the teacher says, well, because it's in the curriculum. Okay, well, why is it in the curriculum? Well, because wiser minds than yours that have determined that it's good for you. I sort of had a conversation like this when I was in geometry class. And that was actually part of my motivation to keep looking a little deeper into this. How would any teacher respond to this? And there is no quick way to do it. That's the problem. There's no easy answer. There's no 3-minute elevator speech that really answers this. And so what I came to believe is that this question needs to be taken seriously, but it needs to be looked at in terms of why society believes that this is a good thing for you to incorporate into the texture of your mind. And that's a serious issue, which needs to be embedded organically into the curriculum itself. So here's an example, and this is actually part of a set of materials that I had the privilege of presenting to sixth graders in Mr. Jacoby's social studies class. And in the Bozeman schools, the social studies historical part of the curriculum actually follows that historical timeline, like you see at the top of that Our Story grid. And so in the second part of the sixth grade year, they're up to classical civilizations, but they have just come out of the study of Mesopotamia and ancient Egypt and that sort of thing. I'm going the wrong way there. So I'm going to leap to a slightly different aspect of this, and that is, if we're going to teach a subject, think about telling the story of it. And that doesn't mean every single detail, but try to capture the primary transformative events in a human context. And then the learner, hearing a story, and stories are very magical and they're very powerful. The learner is able to move into the persona of the protagonist. In this context, as a student, I am Thales. I can see my home in Miletus up here, and the journey that I took as a merchant to come down here and spend 22 years of my life traveling in working in Egypt. That's what Thales did. Born in 624 BC on the western coast of what's now Turkey, but this was Ionian Greece. So here's Greece and the Aegean Sea over here. It's going the wrong way again. So this is what Egypt looks like. It's what it looks like today, and it looked a lot like this back then. I actually took this picture from the cliffs over the temple complex of Queen Hatshepsut's tomb near Luxor. And what you can see here, there's the Nile River. You can see where the irrigation of the fields stops and where the natural land begins. And it was like this 4, 5, even 6,000 years ago. They were irrigating these fields, and that was the basis of that early Egyptian civilization. They had a special class of priests whose job it was to restore the fields after the annual flooding of the Nile receded. They had to be good at it. They had to be quick at it. They had maps, plat maps, and these were the technologies that they used. Recorded maps or records of who owned what field and so forth, and then the capacity to measure distance with a knotted rope and to create a square corner of a field with a 3, 4, 5 triangle. So there's the rope. These are the rope stretchers. They are the priestly class who were the geometers. Thales made friends with these folks. You also see geometry being used in the construction of these massive architectural structures. And I have a theory that these things were created to employ the agricultural workforce when there was no work in the fields for them. Otherwise, as the tale of Gilgamesh warns us, they will go out and get drunk and be a problem. So keep them employed. So that pyramid, the Great Pyramid, has an interesting geometrical curiosity to it. The base, if you measure the 4 sides and add those up, equals 3,020 feet. And if you were to make a circle with a radius of 3,020 feet, that is the height of that pyramid. So they like to put these little mysteries into the architectural work that they did, perhaps as a message to those of us of the future. We have writings. This is hieratic writing, a simplified form of hieroglyphics, but it shows how they recorded their mathematical thinking. What you do not have here are mathematical proofs. Thales actually originates those. What you do have are very well articulated formulas for how you perform some kind of an intended act. This is a truncated triangle, so like a triangle with the top lobbed off of it. And this is the instruction for how you would find the area of this. You can see that a farmer's field could take that shape. And so this is practical knowledge. This is a painting I did. So I want you to imagine now that we are going to travel back to ancient Egypt. And there's a group of people out there, a little bit out of sight, and they are gathered around and they are looking at this configuration that has been set up in the earth. 4 wooden stakes and 2 ropes stretched between them. And if we move close to this group and we listen carefully, we can hear their conversation. So one of them says, "As I have said, Thales, if 2 straight lines intersect, opposing angles will be equal. See here, take a look at this." Thales looks at this and he is puzzled and he says, "Yes, I can see that. That's intuitively obvious. But how would you prove it?" And of course, the Egyptians, being very practical people, they sort of look at each other and say, "What?" And then one of them says, "Well, what a ridiculous question. Why would you need to prove something that's so obvious?" So what I've done in this little vignette, this little story, is I've given you a problem space and the very beginning of a conceptual shift that takes place. And when we look at the history of mathematics, the history of geometry, Thales is the one who asked that question. Now, when I asked this question of sixth graders, showing them that same illustration, how would you prove it? These were the ideas that they came up with. And, this is good. A protractor, you could measure the angles, a cardboard template or a wooden template, make it fit over here and then see if it fits over here, or a transparency. You remember transparencies? Make it and then flip it around 180 degrees and see if it still fits. These are all good answers, and they are all characteristic of an empirical approach to trying to solve that problem. Measurement, observation, and measurement. Thales eventually was credited with 5 theorems, and this is one of them. And it's puzzling, and he was celebrated for it. It's puzzling because it's intuitively obvious if you look at it. So what is there to celebrate here? But that misses the question. It misses the point. The point is, this is the beginning of a conversation that Pythagoras then will pick up, and that conversation continues to evolve for 300 years and culminates in the work of Euclid, that famous textbook called The Elements of Geometry. I'm going to skip over this in the interest of time. So here's a second. So that's one transformative event. How would you prove it? That will be the beginning of formal proof. This is a second transformative event. The Greeks started out with practical problem spaces like you see in this picture in front of you, but under the tutelage of Pythagoras, they refined the problem space, and they did it by a process of abstraction. Now, if you ask people, what do we mean by abstraction? What is an abstract idea? I asked elementary education majors this. They're bright people. They have heard the term before, obviously. But what they would tend to say is, well, it's when an idea is difficult, or it's complex, or it's difficult to grasp. And that's not quite it. So this is an exercise in abstraction. We go outside, we set up this arrangement, and I ask you to observe it. And I did this actually with sixth graders, and I also did it with a group of about 12 of the district's middle school social studies teachers, with similar results in both cases, although the teachers understood it better. Take a moment to observe this, I would say, and then take your notebook and sketch what you're seeing. Make a nice drawing of it. Draw the wooden stakes, draw the ropes, and then some students said, how about the grass? I said, sure, put the grass in there too. And I showed them this later. This is a model, but it shares something in common with the actual. So we're calling this the actual, we're calling this the model. So a typical drawing would look like this. And then I would ask the students when they finish, turn to your neighbor, share your drawing, and talk about this. And here's the question. When you made your drawing from the actual, what did you carry forward and what did you leave behind? So obviously they left behind the material of the ropes and so forth, but the image of it is what they carried forward. Then I asked them to draw it again, but instead of drawing out the rope literally, just draw a straight line. And instead of the stake is there to mark a location. Just use a dot to do that, a point. And then again, the question, what did you carry forward and what did you leave behind? This is an example of what we mean by abstraction. We are abstracting something, that's what we're carrying forward, and we are sloughing off and getting rid of the distractors, the irrelevant parts of the original. Then I asked them, take a look now at the drawing that you made, that abstract drawing, and secure that in your mind's eye. And I want you then to close your eyes and still see it. because that means it is a cognitive phenomena instead of a visual or a thing out there. And if you can do that, then that is what we will refer to as a visual image of two straight lines intersecting. And then I asked them, okay, we're going to do the next step, and that is you're retaining a visual image. Try to manipulate that image. It is still two straight lines intersecting. Make them longer. Change the angles of them in your imagination. And what you're working with now is the abstract concept, a personal concept of two straight lines intersecting. This gets us closer to the mathematical object, which is related to but different from the actual ropes and wooden stakes. What comes next? Well, every one of us has a personal concept, and we are trying to get it to align with what we can refer to as the authorized concept. This is the concept as understood by professional mathematicians and is represented in the curricular materials in the textbook and so forth. Yes, a nice philosophical question. What is the ontological status of mathematical entities? There is one more level, and this is the level of Platonic forms. Plato became so enchanted by geometry, which he studied with the Pythagoreans, and so entranced by the fact that a mathematical proof proves things for all instances. And I'll show you one in a second. But he believed that that means that the idea, for example, of a circle or a line or a triangle has to be immortal. It has to be a permanent aspect of reality, but not in this physical realm where things come into being and disappear, but in another realm. And so he coined the notion of the realm of forms, and he believed that ideas were real. We don't believe that anymore, but philosophically, it was a very powerful heuristic, because as you work with that idea, indeed, that notion, indeed, it seems like ideas are more real even than physical things. So this is a summary document that you're seeing on the right-hand side, and each student or participant in this little exercise got one of these after they had gone through it. And the value of this for a teacher is when you put a drawing on the board and you say, well, this line here intersects this line, you're pointing to a representation of what you're really discussing. The subject matter here is the abstract authorized concept. And students can get a little bit disoriented in the exchange between these various levels. So clarifying the fact that you have levels of abstraction represented in this process creates a high level of comfort for students with the notion of what we mean by abstract ideas, abstract expressions. And I also followed this up with examples of abstract art, which in many cases consisted of forms being wrenched from the real world and just presented on canvas. Okay, so Thales asked this question: how would you prove it? This is what the students came up with, and these would have been the standard kinds of explanations that would have made sense empirically. But yes, instead of trying to perform measurement on concrete objects, we want to consider only the logical relationships. And it was the Pythagoreans who took this saltatory leap into the realm of abstract ideas. And so a line would be eventually defined as that which has length only and no width, which violates common sense and on the face of it seems to be absurd unless you've come to understand how abstraction operates. This is the proof, and it requires that on a single line, like this line here, this, for example, would be called a straight angle. This would be called the straight angle, and this straight angle has now been transected by this line, and so you have two smaller angles, A and B, that make up this straight angle. This is another straight angle, and it has been divided into angle C and angle A. We put those two together. A is in common to both this straight angle and this straight angle. When you remove A from those two straight angles, the remainders, C and B, are going to be equal. Okay, now this is an important point, and if we're trying to move the students sort of organically into this world of pure ideas, why would you make this shift? These are the reasons. It purifies the subject matter, so we're getting rid of the distractors. We're only working with the relevant features. It shifts the strategy from one of empirical measurement to one of logical investigation. This is profound. It sidesteps the uncertainty and imprecision inherent in measurement. You can measure 100 examples of this, and you can do inductive reasoning and say, well, I've measured 100 of them. The results are always the same, so I'm predicting reasonably enough that they always will be the same. But in this kind of an approach, once you have proven it, you've proven it for all cases. And then two more reasons that I think are very compelling. Engagement of this kind of activity serves to develop the mind, and that's the cultural or the liberal educational value of learning geometry. It's part of my answer to that student who says, well, why would I want to learn this? It trains us to see logical relationships in the appearance of nature, and therefore, as a discipline, we acquire a mathematical mentality. It is one of the lenses that we're able to look at the world through. It is a worldview, if you will. And number 6, it gives us pleasure. So there is a deep aesthetic beauty to mathematics if you are looking for it and if you understand that it's there to be found. It's not part of the curriculum. It's not part of what normally happens in a classroom. But I would suggest that it should, because memory and understanding are very much affected by affect, feelings, and emotions. We know that. And so if we want students to be hungry for this knowledge, to acquire it, and to find pleasure in it, that will ensure that it is understood and comprehended and remembered. Okay, so one more example. The angle theorem of the triangle. You take a triangle like this one, ABC. Now, and the proposition is that the interior angles of a triangle add up to 180 degrees, or 2 right angles, as the Egyptians would have said. They did not use degrees. Well, how would you prove that? Here's one sort of clever empirical proof. Well, tear the triangle into 3 separate pieces so that you isolate the angles from each other, and then put them together and see if it forms a straight line. Does it? Well, sure looks like it does. This is the logical proof. And it requires a construction. We're going to extend this baseline. We're going to construct a line parallel to the base through the apex. And then we're going to take into account a earlier proof that you have to have known already, and that is that when a third line intersects 2 lines that are parallel to each other, interior opposite angles are equal. That means this angle up here will be equal to this angle down here. And similarly, B prime will be equal to B. So there you have it. Manifestly, A prime plus C plus B prime equals a straight angle. And this is a proof by logic rather than by empirical demonstration. So the ontological status of this proof is fundamentally different. This is harder to get at. So, students might say, well, why would you go to all that trouble when you can just tear up a triangle? But this requires us to forego empirical demonstrations in favor of deductive reasoning. But the advantage is we've just proven it for all triangles. The proof is exact, it's not approximate, and it applies to all. And then, of course, we have to have this caveat within Euclidean space. Okay, so those are a few demonstrations of what would happen in this part of the curriculum as students are seeking to learn classical geometry, telling the stories of those 17 primary transformative events. Gives us the opportunity to help them navigate the conceptual leaps that have to take place as they move from amateur to from novice to expert, or at least in that direction. There's a little kind of historical summary of those 300 years: Thales, Pythagoras, Plato, Euclid, and then several of the other prominent figures in there. We would have worked in the social studies class off of a more elaborate timeline and biography. But I will say that the cultural effects of Greek geometry were profound because it became a way of thinking. And the Greeks effectively discovered a style of thinking that they called rationality. Once they had acquired it, they also discovered that they could carry that way of thinking into other domains. And so it became part of formal argumentation in natural language. The sophists are the ones who picked up that capability. They taught people how to reason and how to argue effectively. The philosophers thought that they were Philistines in doing so. So there was a kind of a competition between them. But there is historical interest in how this development of geometry came in many respects to dominate Greek intellectual culture as a moderating force within it. Okay, that is it.